Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 721, Accounts Merge. Before we read the question prompt, I just want to say that 78.6% of you that watch these videos are not subscribed to my channel. Now, if you want to get a job in FAANG, you're going to need good karma to pass that interview. And if you don't subscribe to this channel and you watch these videos, then you're going to have bad karma, you're going to fail all your on-sites, and you're never going to work at FAANG. So if you want to get that job, you better subscribe to this channel and have that good karma. Anyway, that being said, let's read the question prompt. Given a list of accounts where each element accounts of I is a list of strings, where the first element accounts of I of 0 is a name and the rest of the elements are emails representing emails of an account. Now, we would like to merge these accounts. Two accounts definitely belong to the same person if there is some common email to both accounts. Note that if two accounts have the same name, they may belong to different people, as people could have the same name. A person can have any number of accounts initially, but all of their accounts definitely have the same name. After merging the accounts, return the accounts in the following format. The first element of each account is the name, and the rest of the elements are the emails in sorted order. The accounts themselves can be returned in any order. Okay, so that's quite a mouthful. It's a little bit difficult to wrap your head around what's going on, but let's look at one of the test cases they provide, and we'll see how we might solve this problem. So let's look at the test case. Okay, let's look at an example. So we're given this input here, accounts, which we are given as a list of lists, and the first element is, someone named John, and they have the email johnsmith@mail.com, and then john_newyork@mail.com. Then there's a second person named John who has an email johnsmith@mail.com, and then john00@mail.com. Then there's a person Mary@mail.com as her email, and then there's a John who has a johnnybravo@mail.com. And we're expected to return John, which is going to be John00, John New York, and John Smith. Mary, there's only one Mary here, so it's just going to be Mary@mail.com. And then this Johnny Bravo John is actually on his own. So let's think about how we might do this. And you'll have to bear with me here because I'm drawing these things out with my mouse. So it is going to be a little bit painful and slow to do that. I don't have, an iPad pen to do it with. Anyway, so let's think about what, our input means. When we're given this list here, we know that it means that John, this person named John, has these two emails. So these two emails definitely belong to him. So we know that there is some connection between the email, John Smith, and, the email is connected to John New York, right? We know for a fact that these are connected, but we don't know, other, Johns that might be connected. Okay, so these are connected for sure, right? So we can think about these as being connected. And then we have this other John, and we have, John Smith. Oh, wait, we've already seen this John Smith. So that means that this John Smith is also connected to this email, John00, right? So these two are also connected. And then we have Mary, who has, Mary@mail.com. So we'll just write Mary, and we won't write the @mail.com. So we have this Mary email, and then we have this, Johnny Bravo email. So Johnny Bravo. Cool. So, as you can see, this sort of looks like a graph. Although, there is some disconnections here, but we can see that there is some connection between this John Smith and then the John00, because they both have the email John Smith. And if you haven't realized already, this is actually going to be a graph problem. So what we want to do is we want to take our accounts here and we want to turn it into a graph that we can actually use and traverse. So for example, if each of our emails here is an actual node in the graph, and we know that everything, in its original list is connected to it. So from, John Smith, I can reach John00, and then from this John Smith, I can reach John New York. Then what we want to do is simply, for each edge in our graph here, if it hasn't already been visited, what we want to do is simply do a DFS and search all the possible connections we can get, and that's going to be the actual emails that are linked to each other. Obviously, if there's like a disconnect here, then, doing the DFS, this will never reach here because obviously they're never connected, and this will never reach here, so they're never connected. So essentially what we want to do is for every email on our graph, so we can think about it. Okay, so like this would be one email This would be one email. This would be one email in the graph. This would be one email. This would be one email. We want to go through all of them. So say we start at John Smith, and we can see, okay, what are the connections to John Smith? It's going to be John New York and John 00. So what we're going to do is, we're going to traverse this. So this is going to be like one person's list. So from John Smith, we're going to try to go into John New York and then go to all of its, connections. Obviously, we don't want to go backwards. We need to maintain like a visited set to make sure that we don't get caught in an infinite cycle. So then from John New York, we'll try to go to all of its connections, but it doesn't actually have any other than John Smith. And since we've already came from there, we don't want to do an infinite cycle. And then from the John Smith, we can also go to John 00. And that way, we'll DFS into all of its connections, but it actually doesn't have any that isn't John Smith. So we're not going to go backwards because that would be an infinite cycle. And then we'd go to the next element in the graph. So that would be this John New York, but we've already visited as part of, going to it from John Smith, so we don't have to go to it again because then we'll just have duplicates here. And then the same thing, okay, we've already seen this John Smith, that's what we started with. This John 00, we've already visited as part of this DFS, so we don't need to visit it again because that would be a duplicate. Then we get to this Mary, we can see that it doesn't have any connections, so it's just going to be that lone email for Mary. And then same with this Johnny Bravo. Even though this guy has the name John, it's not actually connected to the other Johns because there's no link between this Johnny Bravo email and any other John email in the graph. So that means that this John and the other John are actually two different Johns. They have the same name, but they're different accounts. And as we can see, that's how our output should look like. Okay, so that's a little bit confusing. How are we going to build the graph? How are we going to do this? I think that instead of me trying to draw this out with my mouse and making it extremely painful for the both of us, what is going to be easier is actually if we go to the code editor and I will write the code and I will walk you through it line by line so you can see exactly how to do it. And I think it should become a lot clearer. But essentially what we want to do is we want to figure out some way to take our input here, which is our list of lists, and we want to transform this into a graph. And we want to use this graph is to do a depth first search. And essentially that way we're going to build all of these connections because obviously the DFS will give us all the possible, emails we can reach from an email. And then, we'll need some way to look up from an email to the name. So we'll have to probably maintain some extra data structure to do that, just so we can know who the final person is. And then from there, we will do our DFSs for each of the nodes in the graph. We'll maintain a visited set to make sure that we don't, get caught in an infinite cycle. And, we will eventually converge at this answer here. So that is a little bit hand wavy. Now let's go to the actual code editor. We'll write it line by line and you'll see exactly how we're going to do it. And it should be really clear. This is a really simple graph problem. All you need to know is just how to transform it into the graph and then how to actually do the traversal, which is just a relatively straightforward depth first search. So I'll see you in the code editor. Let's write the code. Okay, welcome back. Now we're going to write the code. Remember that the first thing that we need here is actually going to be to build our graph. And for our graph, we're going to need to maintain a mapping, which is going to be the key as the email, and the value is going to be all of the emails that it's connected to. That way, for every email, we know all the possible, edges we have in our graph, and we can do our traversal that way. So let's set up this data structure. So we're going to say graph is going to be equal to collections.default dict, and here we're going to use a set. And the reason that we want to use a set is because there's going to be a lot of duplicates in this, in the list of items, because obviously there's going to be emails that are duplicated. So we don't want to have to basically traverse things that we've already done. We want to use a set to maintain a unique collection of emails that we can reach from a given email. So that's why we're using a set here as the value for our dictionary. And what we're also going to need, and you'll see why we need this later, is going to be actually a map which takes an email and maps it to the name. And the reason that we need to do this is, remember that we need to return our solution as the first element should be the name. So we need to be able to go from an email and figure out the name so that we can return it in this correct output that it wants. It's really strange. It needs to be sorted as well, but that's what the problem asks for. So that's why we need this extra data structure, that whatever node we kick off the DFS from, we need to find the name of that person And remember, the nodes in our graph are going to be the emails. So we need to go from email to the name. So that's why we need a map like that. So we're going to say email to name is going to equal to just an empty dictionary. So now we actually need to build the graph, and we're going to get the data out of our accounts here, which remember is in this form of a name and then all the emails for that one person. We know that these emails are connected to each other. So we're going to say for account in accounts, and remember that the first element in this accounts list is always going to be the name. So we're going to say name equals account of 0. And we're going to say, okay, so now we need to go through the emails. So we're going to say for email in account. So starting from the first element, what we want to do is we want to now build the graph. And what we want to do is basically we want to connect all the nodes to each other. And instead of doing it, every single node connected to every other node, we're actually just going to connect them to the first node, and then from the first node you can go in, just so we don't increase the complexity of our graph here. We just want everything to go through that first node. It's going to cut things down and make it actually a little bit simpler. Otherwise, we'd have to do for every email, it would have to be connected to every single one, and it's just going to blow up the actual space that we need here. So we're going to keep it simple and just connect everything through the first node in our emails list, and then from there you can just go to the other ones. So we're going to say graph of email. So we're going to add to the list of emails that you can reach from this particular email. We're going to add the first email. Remember, we said we're just going to be going through that first node, so we don't have to do it to every other single node in the graph for this email. And then we're going to say graph of account 1. So we need to do the reverse connection dot add email. So that means that the first email will basically have all of the emails in the graph. And that way we can just, save space for the other ones. Okay, cool. So actually the last thing we need to do is just say for, this particular email, what name does it correspond to? So remember, all the emails in this, account 1 are going to be for the same person. So this John Smith, John New York are all going to be of this guy, John. So we need to just set them equal to whatever the name was. Cool. So now we've built our graph, and what we need to do now is actually, build our results here. So we need to go through the graph, perform our DFS, and we need to build, the result. So, the result is a list of lists here. So we need to define that data structure for it. So we're going to say res, just going to be an empty list. And remember that we're doing a graph traversal. So we do need some sort of visited set to make sure we don't get caught in an infinite cycle, because remember that, all the emails are linked back to this account 1. So it is possible to get into an infinite loop if you don't look for it. So we're going to say visited. So it's just going to be an empty set to keep track of where we've been. Now we need to go through our graph. So we're going to say for email in graph. So this email obviously represents a node in the graph, and then we're going to try to go to all of its connections in a depth-first search manner in order to basically just find all the connections for that given email. And then we're going to add things to the set as we go along. So we're going to say if this current email hasn't been visited before, then we need to do some work here. So we're going to say if email not in visited, visited, what we need to do is we need to set up our DFS, and I'm going to do it iteratively instead of writing a recursive function. So I'm just going to use a stack here. So I'm going to say stack, and I'm going to put the email in there because that's what we need to process. And then I'm going to add this email to my visited set to make sure that, again, I don't get caught in that infinite loop. Now what I need to do is I need to build out all of the emails that I can actually reach from this email. So I'm going to need to keep track of that. So I'm going to say local res, which is just going to be all the emails that I can reach from this email. It's just going to be an empty list. And what I want to do now is actually perform my depth first search. So I'm going to say while stack. What I want to do is I want to get the node out. So it's going to be node equals stack.pop. So I'm going to get my next thing to process. And okay, so that means that this node is accessible from this email. So I need to add it to my result because I've seen it along the path. So I'm going to say local res dot append the node. And what I'm going to do now is remember that it's a graph. So I need to go to all of the nodes that I can from this particular node. So I need to basically traverse all the edges, and then from each of the nodes that I can reach, then I need to go into their children and on and on and on. So I'm going to say for edge in graph of node, I'm going to say if that node hasn't already been visited, then I want to explore it. Obviously, if it has been visited, we'll get caught in an infinite loop. We don't want that. So we're going to say if edge, not in visited, then what I want to do is I want to say stack.append. Not edge. It should be edge here. So I basically want to add that edge for further processing. So I'm going to add it to the stack, which represents kind of like our DFS here. And then I want to add that edge to our visited set, make sure we don't get caught in an infinite cycle. And then we want to do this while we have a stack. So basically, perform the DFS, go to all the possible nodes that you can from our original email here. And, we'll do that DFS and we'll be populating local result as we go. So what we want to do now is, when this DFS ends, so basically when the stack is empty, we have processed everything that we can. Our result here will be storing all of the nodes that we saw along the way. And we need to add that to our, global result here in the correct format. So remember that the format is going to be the name of the person that these accounts belong to, and then the accounts in sorted order. Why it wants them in sorted order, I have no idea, but it wants them sorted, so we have to do it. So what we want to do is we want to say res.append, and here is where this problem gets a little bit clown towny. So remember, we have this email to name, and we need to basically fetch the name of the email that we started with as that first, element in the thing. So we're going to say email to name, and we're going to be looking up with the email here. And then let's make sure we don't mess up our kind of parentheses there. Plus, now we need to sort the local res for whatever reason they want it sorted. Don't ask me why. And that's, basically going to be the solution for that given email. So we will have explored all of the emails that can be reached from this email. We found who they were linked to. We found all the emails they were linked to, and then who the name was of the account. And that's going to be basically what we want to do. And we're going to do this for every email in the graph. Remember that we are maintaining a visited set. So if a node comes up that we've already visited, we're not going to explore it again. It's already been taken care of somewhere in our DFS at some point. So the last thing that we need to do is simply return our result. So let's make sure that I haven't botched this somewhere and submit it. And cool, it works. And we actually beat almost 100% of people on the runtime complexity. So that's really good. Okay, the last thing that I want to do is actually just touch on the time and space complexity. So let's think about what that might be. Okay. So we wrote the code, we submitted it, we saw that it works. Let's think about the time and space complexity. So this problem is a little bit tricky to kind of derive this, but it's not so bad. So let's figure it out. All right, so what are we doing here? Remember that we're doing a, DFS through our entire graph. So in the worst case, we're basically going to have to traverse this graph, right? We have to visit all the possible nodes. So what this means is that it's going to take, big O of n time to traverse the entire tree. But what happens, in the case that there's like multiple accounts for a person, what is the actual worst case? So in the worst case, actually all of the accounts are going to belong to one person. So it's just going to be like John and then all of their, emails. And what we're going to have to do is we're going to have to visit all of these, edges and basically build out our result. So if we say that n equals the, number of accounts that exist in our tree here or in our graph. So basically, the number of like people here. And then we can say that k is going to equal to the max number of accounts per user. I guess this should actually be email, max number of emails per user. Then, to traverse the tree, it's going to take, big O of nk time. So, when there's one account, it's just going to take k time because we have to basically traverse all of the emails. So to do the actual traversal is going to take big O of nk, right? So for each email account that we have to traverse all the emails. So that's why it's nk. So that's going to be the actual like graph traversal part. Now, remember that we're sorting here. So, this sort operation is going to be, okay, well, how many times do we have to perform this sort? We have to perform this sort, basically, n times, so the number of, distinct accounts there are in the graph, so like, this John, this Mary, this John, we'd have to do it n times log k, because we're sorting over a list of length k, which is the number of accounts that a user has. So it's going to be, times n log k. So our like global time complexity is going to be, n times k times n log k. So this is going to be, the time complexity here, and that's a little bit of a weird one. So what is the space complexity? Well, the space complexity is going to be dominated entirely by our graph here. So to build, our graph, in the worst case, like we said, all of the emails are going to belong to one person. So, our graph is going to have to just store all of the accounts that were basically given to us in accounts. So in the worst case, this would be like, one key here. So it'd be like user one, and then they would have all the, emails, and we'll just do like 1, 2, 3. So all of them would belong to them, which is just going to be, in total, it's going to be n times k space, where remember, n times k. And why is it n times k? Remember, n is the number of accounts. So that means that this is going to be the number of keys in our dictionary. And if k represents the value of the emails for that user, then there's going to be n accounts, and then each account is going to have k values to it. So that's why it's n, big O of nk for the space here, which is going to be represented by our graph, which is going to dominate the space complexity here. So that is your time and space complexity. Just to recap, it's going to be n times k times n log k for the actual time complexity, and the space complexity is going to be big O of n times k, where again, n is the number of accounts in total that we have, and then k is the maximum number of emails for that user. So just basically their list of emails, however many they have in there. So that's going to be how you solve this problem. This is a really cool one. I quite like this one because it is a graph problem, and those are definitely my favorite. It is a little bit interesting to wrap your head around, but I think that once you realize that you need to just represent this, list of accounts given to us as a graph, and then you just want to do a DFS traversal to figure out all of the accounts or emails that belong to an account, then it's pretty straightforward. I think the code is quite simple and it's quite intuitive, so hopefully you were able to follow. And yeah, hopefully you enjoyed this video. If you did, please leave a like. Remember to subscribe so you have that good karma and pass your interviews. Leave in the comment section below what other problems you want to see. I'd be happy to make these videos for you guys. Just tell me the problem number or the topic that you want me to cover, except dynamic programming. I'm sorry, I hate dynamic programming. Yeah, and I'll get back to you. So anyway, thanks for watching. Have a nice day and happy coding. Bye.